All right, so we're starting 1.1 function relationships part 2. So based on our part 1 where you did it stick and our gallery walk, we need a little more review. Agreed? All right, so let's dive into this. We're going to start with linear function. And a linear function is a relationship between two quantities. Okay, what do we usually call those two quantities? X and Y. Okay, and the key thing is it's with a constant rate of change. A constant rate of change. Okay. All right. Now we're going to talk about the characteristics of it. So the characteristics of a linear function, the number one thing is it has a constant rate of change. Does anyone remember what that constant rate of change is called? Say it again. The slope. Good job. The slope. That's our constant rate of change. Okay. The other thing to remember is that the graph is a non-vertical line. Okay. And the other thing is there are 3 ways to represent the function. Okay. What is the number one way you guys remember the function? Y equals mx plus b, right? The number one thing that's written over there on that little poster is y equals mx plus b. Okay, so we're gonna write, that's our first way, but because we're talking about a function, we're gonna write f of x. When we write y equals, that's an equation. Okay, when we typically talk about a function, we try our best to write it as f of x. So we're gonna write f of x equals mx plus b. Okay. The other way of writing it is in standard form. Standard form is ax plus by equals c. Anyone remember standard form?
No. I do not remember. Oh, I remember that. I remember it.
Makes sense? Makes sense. Ax, capital A, capital B, capital C. And then the last way to write a linear function is in point slope form, which is y minus y1 equals m times x minus x1. Okay, so those are the characteristics of the linear function. Now we're going to do some examples. Let's see. Rosa, what's your favorite number? Rose, what's your favorite number? 8. All right. So our example is going to be f of x equals 1/8 x squared. Not x squared, Miss Jones. What are you doing? 1/8 x minus 8. Is that a linear function? Yeah. Yes, it is, right? Okay. I want you to draw your best graph of a linear function. It does not have to be the same graph as mine. You're drawing your very, very own. So you're going to draw your own best representation of a linear. It can be a positive or a negative linear, whatever your heart tells you to draw. Okay, next we're going to draw a table, because that's another way of representing it, right? So with a table, the key thing is how your x values change and your y value change. They have to be consistent, right? So if I have X is 1 and Y is 2, and I have 3 and 6. Okay, we'll do 6. Uh-oh. 3 and 6. What would be my next numbers? Good job. Why did you say 5 and 10? So we, on our X's are increasing by 2s and our Y's are increasing by 4s, right? And that means our slope is what? Other way. 4 over 2. It's the change in your Y. Remember, slope equals your change in your Y over the change in your X. So how did my Y's change? By 4, right? How did my X's change? And what is 4 divided by 2? 2. So my slope is 2. All right, what will be my last number to fill in my table?
It would be 7
And 14. All right, real world example. Can anyone think of a real world example that has a slope? Your weight can be an example. What else? Consistently depositing money into your bank account. Any other example? Your what if, how many of you by show of hands have a job? Have a job. Yeah. Your hourly rate, is that not slope? It is. Your hourly rate at a job is a slope. That is the slope of your job. Okay. So I'm gonna write hourly rate. That's gonna be my real world example for slope. All right. If you're driving, your miles per hour, that's
Your
also
gas.
your gas. How much
Is it your height?
your price per gas? Huh?
Is it your height?
Your height?
No, the people should not. Exactly. I told y'all. From like
Okay.
ages, like a baby, like
I don't think it goes up and
it goes
down.
up. Oh, it's not.
It's not constant. We would all be giants.
I made it.
All right. An example of why that's not true. My son grew 2 inches this summer, and like from May to August, he grew 2 whole inches. Versus last year around, from August of school year to May, he only grew 1.5 inches. So it's not a constant rate of change that's happening. So I keep his height. That's why. All right, here we go. Non-examples. So non-examples would be
Oh, your height.
well, growth rate. It is, but I will tell you, linear functions are used to make the projection of it. So your projections of height that your doctor says, this kid is gonna be about 5'10". That's usually a growth rate. So, yeah. You've never looked at the growth rate chart? Your projection? Well, my son's doctor did. He's projected to be at least 6'4". What his projection is.
Be allowed to exist.
All right. If I put 6x squared, is that a linear? It is not. If I draw, or I could have drawn squiggle. Is that linear? No, it is not. Okay. So your non-example can be anything. It doesn't have to be mine, as long as it doesn't fit the definition, characteristics, or examples we have, right? Make sense? All right. What are your questions about linear? None at all. We feel that's our safe zone. All right. Guess what's next? Quadratic. All right. So for our quadratic, the definition is, let me write it in a brighter color. There we go. It's a relationship between how many quantities again? 2. And what do we call those quantities? X and Y. My Y got a little weird. Okay. However, the difference here, guys, the difference is with a linear rate of change. Okay, the key thing here is a linear rate of change. The reason why it's called a linear rate of change is because you can connect any 2 points on the quadratic with the line. And when you get to calculus, you'll learn a little bit more about that special line. So next year. All right, so the characteristics are they have a linear rate of change. Okay. A good way to think about it, it would be called, it's like an AX plus B situation. Okay. The shape, anyone remembers what the shape is called? Of a quadratic. There you go, a parabola. Spelled like parabola. A parabola. And so you either have a positive, a happy, positive parabola, or you have a sad, negative parabola. I know y'all had to hear the word parabola in Algebra 1. Yeah, y'all did. Y'all heard the word. Yeah. All right. There are three ways to write the function of a quadratic. Our most common way is called its standard, which is f of x equals ax squared plus bx plus c. The people who make your shopping experience easier use it. I said the people who make your shopping experience easier use a bunch of math. All right, then we're going to write in what's called vertex form. So vertex form is f of x equals a times x minus h squared plus k. That's called vertex form, which may or may not have been addressed in Algebra 1. And then our least used form is called root. It's our root form. So f of x equals, and it's a times x minus r sub 1 times x minus r sub 2. No. Yes. As we get deeper into it, you will. You'll be surprised what your brain will do. We're going to stretch your brain. Okay? You want to keep an open growth mindset, right? We always want to grow and be willing to grow. All right? Examples. So we're now going to do an example. I need a favorite number. Diana, what's your favorite number? 7? All right, now we're working with 7s now. So is f of x equals, we're going to do 7x squared plus 7/10 x minus 7. That's a lot of seven. She said her favorite number was 7. We rolled with it. All right. Is that a quadratic? Yes. What makes it a quadratic is that the highest exponent is a 2.
I don't see that.
And then
Oh.
This little guy makes me a quadratic.
Oh, I see.
Okay. If that wasn't there, then it wouldn't be a quadratic. But because my highest exponent is a 2, I am a quadratic.
what would it?
No.
If you took away this whole piece, I would be a linear. It would be a linear.
So what if the exponent is higher than 7?
Then we learn if the exponent is higher than a 2, you mean?
Oh, then you have to find it.
Then it's called a cubic or a quartic or a quintic or there's a bunch of more that we'll learn about. Don't worry.
Oh, because the 2 will be 2D, right? So we're not-
2 is just quadratic. It's called a quadratic function. All right. Now we're going to, can someone give me a real world example of where a quadratic may appear, whether it's in function or, yes.
Like throw a ball up.
There we go. Sports. So for example, the trajectory of a ball, right? A ball. So whether I'm kicking the ball, shooting the ball, it's gonna do some type of upward movement because what goes up must do what? Come down. Okay. All right. Now I want you to draw your own version of either a happy or sad parabola. We're gonna create a little graphy graph. There's my graph. And then the last representation we need is the table. I'm gonna do simple table. I'm gonna just do our perfect squares. Okay, what is 1 squared? 1. What is 2 squared? What is 3 squared? What is 4 squared? 16. And if I was to continue, this represents a quadratic because I am squaring each x value.
Yeah, I understand.
Get it?
Wait, so every X value in the quadratic
Is it squared? And then multiplied or added, huh? Then you have to square it, because remember we follow PEMDAS. And we square, then we multiply, add, or subtract. Your initial, your x is squared. Yeah. All right. Okay, now anything else? Your non-example, draw a non-example. Whatever you want, as long as it doesn't fit our definition, our characteristics, or our examples we have. So draw a non-example. Non-example. Someone asked, Oscar, was it you? If I said, what if my exponent is anything other than a 2?
Yeah,
Then it's not a
Right.
quadratic. So would that be a non-example?
yes.
There we go.
Wait, is this one?
Yep. Just a straight line? It is. All right. I'm gonna draw what's called a sine wave for y'all to the best of my ability. You'll learn more about that. Pretend that that's perfectly drawn in pre-cal. Okay. All right. Questions about quadratic? No? All right. Last but not least is exponential. All right. Exponential is a relationship. Shh, guys, there's a lot of little talking. If a seating chart is needed, it will be given. All right, a relationship between, that got weird. two quantities. And again, our two quantities typically are X and Y. Now, the difference here, instead of a rate, it's with a linear rate, not linear, a constant ratio with a constant ratio. With a constant ratio of growth. There we go. Okay, and is it too late to put a slash? Decay. Because exponentials don't always have to increase, they can also decrease. Like, have you ever heard someone say, oh, they declined exponentially? Exactly. Thank you. Someone knew where I was going. That means it happened really fast and people lost their money.
Yeah, value basically.
Yeah. All right. So characteristics of it is the constant ratio instead of a rate. So now we're dealing with a ratio, not a rate. It can be a growth. So you can have a growth, which means your graph is doing something like this. Or you can have a decay, which means your graph is doing something like this.
Or just slowly.
No, it's rapidly.
Oh.
It's quickly happening. It's a quick decline. I mean, it can be a relatively slow, okay? It has what's called an asymptote. It has asymptotic behavior. I think I spelled that right. Asymptotic. I think that's right. Behavior. Asymptotic. Okay, that means it has a limit, a threshold.
These are bigger words than English.
What? I'm pretty sure I spelled it right. Asymptotic. All right, and the ways that we can represent it is f of x equals a times b to the x. A times b to the x. Notice now that x is our exponent, which is why it's called an exponential. Because x is the exponent. Okay. What? X is your exponent, which is why it's called exponential, because your exponent is the x. All right. All right. Our examples of exponential. Yes, in a transformation. Well, yeah, we have a whole unit on it. Don't worry. So we have f of x equals 2 to the x. It doesn't matter what my base is, as long as x is what? The exponent, as long as x is the exponent. Capiche? You know, in response, you're supposed to say capisco. Nuh-uh. We looked it up. It's not. It's just that some teacher decided, and then we all just kept running with it, that you say capisce, capash, but it's like capisco, meaning I understand, because it's Italian. I think I said that right. I'm not Google. I'll have to make Google say it again, but. All right. So next we're gonna talk about the table of it. So if I have an exponential table, So notice I'm at 1, 2, we're gonna keep it simple, 4, 5, right? And I think I'm trying to save money, so I'm saving a lot at a time. So I put $1 in on the first day. On the second day, I put $2 in. On the third day, I put $4 in. On the fourth day, I put $8 in.
You're talking about saving money.
And I'm gonna keep adding more and more. Uh-oh, my 8 disappeared. So on day 5, I put 16 in. So I am not doubling it. I'm multiplying by it 2 every single time. Do you see that? So every single time, that's why it's a ratio. I'm multiplying by 2 every single time on the next day. So what would day 6 be?
32.
There we go. Okay, I don't either. These are pennies.
Oh,
These are pennies. For my pennies. Okay, yeah, I'll go really fast. All right. So what my table would look like, or my graph, again, I am doing what? I'm increasing, right? So my money is going, ooh, I'm getting there. I'm like, ooh, real quick, real fast. So if I was here, it's going like this. Uh-oh. Mine do too. Wait till you pay bills. Okay. What we had an example. What was our example? A good example of an exponential in real world. Stock, stocks and the growth or decay of them, right? Ideally, people want their stocks to do what? Grow. I feel like stocks is like legalized gambling, and I just no, there are notes, babe. Yep. All right. And your non-example is anything that doesn't fit in these 3 boxes, right? So a non-example would be a linear. So I could write x plus 5. Is that an exponential? It is not. I could write f of x equals x squared. And again, my x has to be the what in order for it to be exponential? The exponent. The x has to be the exponent. Okay. I can draw a straight line. Is that exponential?
What if quadratic also be a non-example?
Yep, a quadratic would be non-example if I drew a parabola. All right. Okay. Those are our 3 functions. Okay. You're going to need these notes for our Desmos activity tomorrow. Got it?